Good afternoon, everyone. Welcome to our Petuum podcast. We have a couple special guests today. The first, Adil, maybe you should introduce the first special guest because I don't know, he might be a little cuter.
This is Kaizen, and he's been complaining about his sleep schedule recently, and so he's decided to jump into this podcast. Maybe he'll fall asleep if we
He's
talk.
an ML expert as well, right?
He's not yet. Yeah, he's more of a Kubernetes guy.
Got it. Fair. Well, our main guest is an ML expert. His name is Mayank Kejriwal. Welcome, Mayank. Good to see you.
Good to see you. Glad to be here.
Mayank and I went to business school together, so we have been friends for a while. Mayank was the first person to teach me what a knowledge graph was and how it worked.
And I have a T-shirt, to commemorate.
Julie knowledge graphs. Okay, here, I'll make everyone's faces larger. Good visibility.
Great.
Each other. Mayank, maybe you can tell us, and I'm Julie Bills. I'm the product marketing manager here at Petuum. And we're excited to talk to Mayank a little bit about what he's been working on. There's a particular project that I'm interested in called Thor, and just MLOps in general, different problems that you had when executing Thor. We've been working on end-to-end MLOps platform here at Petuum. So as we've been building it, we've been talking to different customers and different use cases for ML teams and trying to uncover what exactly their pain points are so that we can solve them. So we'll see if there are any overlapping issues that we've had with some of our other customers. But maybe you could tell us a little bit about yourself, Mayank, where you're from, what your journey was to AI ML.
Sure. So I'm Mayank. So I'm currently a professor and research team lead here at the University of Southern California. I was also a student, as Julie mentioned, we went to business school together. So I was a student in one half of campus and then a professor in the other half, which was a lot of fun. So I am originally from India, but I have been in school forever, I should say. Came here to the US when I was 19 years old, did my undergraduate, my PhD, all of that before landing in USC. I moved westward, consistently from India to my undergrad to my PhD to now, and now I'm on the coast. So
you went to Austin, right, for undergrad?
For my PhD, yeah.
Adil is located in Austin right now.
Oh, that's great.
That's a good place.
It is. It really is. So it's so it's been quite a ride, and I like to pinpoint the time when I came into AI with an undergraduate course. So I took an undergraduate course on AI. I was an electrical and computer engineering major. This was my first foray into AI, and it's like a survey course. You take it during your junior year. It's offered in the computer science department. And, you really get to see what AI is, what the history is, what all the different tools are, and so on. And I just fell in love with the subject, got research experience and didn't look back since then. So it's been
really? You've been full steam ahead on AIML?
Full steam ahead, 2011, spring of 2011, took the course, full steam ahead since then. 2012, took the course on machine learning, then went to Singapore for the study abroad, came back, joined the PhD, and went properly into research. So it was a lot of fun. 2011 was a very major year because knowledge graphs, which are very intricately tied with what I do, was, one would argue, invented in 2011 with Google. So this is an exciting time to be in AI. The last 10 years have been very exciting for my field, but in general for AI, it's been very exciting. And at USC here, my work is funded mainly by DARPA, but also corporate grants, philanthropic grants, a number of funding sources, but primarily by DARPA. And we are interested in, moonshot projects. These are 3-4-year projects that are, and you'll hear about one of them today, where we're trying to solve a really big problem that is a 10-year problem or a 15-year problem, and we're just trying to get to the next stage of it. And so these are really fun, collaborative, multi-institutional projects where we really bring the best of the technology to bear and then push the best, push the envelope a little bit more after that. So that's what I work on even now. I'm interested right now in artificial general intelligence. That's kind of my obsession right now. How do we get AI to become more human-like, a single AI to become more human-like? more trustworthy, almost like a colleague as opposed to a system. And there's a long way to go in that. So
Yeah,
that's
I read
kind of what
in
I'm
your
working on.
core paper that you had some reasoning involved in that. So that'll
Yeah.
be cool to talk about. Maybe you could, so you literally wrote the textbook on knowledge graphs, right?
I did. I co-wrote it, but I was the first author.
So maybe you could just share briefly, in case there's anyone else out there, like young me, that didn't know what a knowledge graph was until Mayank taught me. Maybe you could tell me a little bit about the core of that technology, how it relates to ML. And then maybe
Yeah. I mean, it's actually a really simple way to describe it. So, think about a knowledge graph as, when we as humans communicate knowledge, we tend to do it in natural language, right? So I'm sort of, communicating knowledge right now, or, insofar as I believe it's knowledge, and it's going, through natural language. I am speaking in natural language, which is English. People are listening in natural language. They are automatically able to convert what I'm saying into entities, relationships, facts, right, and beliefs, and all of that, and it's happening in our brains in this magical manner. And so how do we get a computer to do that, right? So how do we get a computer to understand that a person is a person, that San Jose is a location, that Julie is a person, Mayank is a person, that Julie works for this organization, Mayank works for this organization, this is our job titles, this is what we do. So there's, all of that can be understood to be knowledge. It's entities, it's relations, it's facts. And a knowledge graph is this structured, formal way to communicate that knowledge to a computer and to represent that knowledge so that a computer can actually reason about it and can understand it, in whatever way machines can understand. So, and that kind of opens up, an entire area of research, which is why we wrote the textbook on this, which is, given natural language, how do you extract the knowledge graph? Inevitably, it's noisy. So how do you clean up the knowledge graph? How do you use it in downstream systems? What are the applications? What are the ecosystems? All of that. And I should just say that, the term knowledge graph, I believe really originated with the Google knowledge graph in 2011. There's a very famous blog post that is still available for everyone who's interested. It's called Things Not Strings. That's the title of the blog post. And what the Google VP who wrote that blog post was trying to express was that, to a computer, everything is a string. So the natural language that we are communicating in would be a string, which is like, this long string in quotes, a stream of characters to the machine. So how does the machine actually extract knowledge from that and know that this is a thing, this is a relation, and so on. And so Google did that. And as a result, its search has gotten a lot better. And many other companies have done that since then, including Amazon, including a number of other companies. And they've really seen benefits from this. So that's kind of what the field is all about. It's gone through 10 years now. It's entering its teens. And we would argue it's fairly mature, but it's getting better with each year.
So this knowledge graph architecture is at the core of Thor, right?
Yes.
So maybe you could tell us a little bit about what Thor is, what it stands for.
Sure. And can I share my screen?
Yes, I believe I've given you permission to do so.
All right, so let me go and do that. Okay, just give me a moment. All right, so here we go. And, I won't go to full screen just yet because I want to move around this and hopefully it's visible.
Yes.
But yeah, this is the architecture of Thor. And, this looks like sort of this nested architecture with lots of boxes inside it. But the best way to understand what Thor is to really start from something like this, right? So, many people will not recognize what this language is, but it's actually Uyghur. It's spoken in northern China in the Uyghur region. And, this is a language which most of us would not understand. Now, let's imagine that an earthquake has broken out in northern China, which, it often does. It's an area that is very prone to earthquakes. And, through SMS, through text messaging, through some kind of social media that is local, folks are sending out messages in this local language. And you can see there are some numbers in here. There are years, there's NHK, and, there's all of this stuff, and it's all time-stamped. Well, if I was the Red Cross, or if I was a foreign, or even another government that does not speak this language, I would need to really understand what is going on here. And I don't have enough time to learn the language, right? So I need to go in and I need to understand, I need to gain situational awareness is what we say, of what's going on in the ground. And situational awareness is who, what, where, when, why, how. That's how we can think about it. So, what is going on there? How did it occur? Who are the people who are in need, right? And so on and so forth. And so what Thor does is this. So the system that you saw goes from what you just saw to something like this. And this is an interactive browser where you can see that we have the original messages on the left-hand side. And what we have managed to do is translate this. You don't see the translation here just yet, but this would get translated. And then a sort of a knowledge graph, what we call situation frames, would get extracted. This would tell you, okay, if there's a need type, what is the need type? What's the location? This is, you can sort of see here that there's a very high density in northern China because most of the messages are coming from here. There may be some other messages that were noisily tagged, and so we're seeing them from other places. They could genuinely be from other places also. But the whole point is that we can work with noise because now we are seeing this interactive browser where we can go in, we can explore, we can see where the problems are, we can even read the translated messages. And so all of that is due to this system. And you can see here in the middle that the knowledge graph, what we call the knowledge base here, is in the center. This is really the infrastructure, that is ingesting a lot of inputs and then is using a data access API to provide outputs to the user interface. So that's kind of the very high level overview of what Thor can do and why the knowledge graph, where the knowledge graph sits right in the middle of Thor.
Let's do an even higher overview level of Thor. So what was the project exactly? What pain were you trying to solve?
So the pain we were trying to solve was that, so we started from the premise that there are many low resource languages in the world. So these are languages for which Google Translate does not work. For some of these it might work, but even if it does, it's really bad. And these are precisely the regions where if a disaster strikes or there's a geopolitical situation that arises, it could be very unstable and you need the Red Cross and other organizations to move in and provide aid as soon as possible. So these are very vulnerable regions and they have languages that are what we call low resource languages. Low resource here means that we don't have good tools for working with those languages. Many millions of people may speak the language, but we don't have the right computational tools. So the main question that was addressed by Thor was that if a disaster breaks out in one of these regions and where the main messaging and data is coming in a low resource language, how can we build a system that provides situational awareness within 24 to 72 hours of that disaster breaking out? So this was the pain point. This was the problem that we were trying to solve. And everything you saw in that box was in support of that. So everything from very rapid machine translation to having a user interface that non-technical users could actually use. They don't need to know programming. They would literally just play with the user interface. To all the other things, including where's the problem, what are the needs, how much food should we provision, where should we send evacuation personnel, and so on and so forth. So all of this is related to situational awareness, because if you get good situational awareness, then you can act on the situational awareness. So we go from this raw body of messages to something that provides situational awareness in English or a major language that the Red Cross or some external entity can understand, to acting on the situational awareness. And that part is usually local infrastructure and doesn't involve AI and technology as much. So our main interest was the first part, which is how do we go from the raw data to situational awareness.
I have many questions. So the end user for that, so that GUI has all of your work abstracted so that the end user can be someone who's non-technical. Yeah,
exactly.
So what is the end user, like a dispatch, at Red Cross, or like what kind of
So that would be one use case. Another use case are US intelligence experts, who may be interested in geopolitical uncertainty and need to understand what's going on. For them, it might be less urgent, but sometimes the need is very rapidly evolving, right? So that's another situation. There are organizations like AFRICOM. So this is like all in caps, AFRICOM with an M at the end. I forget what it stands for, but it's kind of like the Red Cross type of organization that is mainly interested in the African subcontinent for geopolitical intelligence and other situations. So yeah, it's all of those, and intelligence analysts, 2 people providing aid, and anyone in between.
So you're building an ML system that can be abstract enough for basically anybody to use the insights.
Yes, and it really is very easy enough to use. And so let me just show a very brief video on this. And so, this you can see this is actually focused on Mozambique, and this is the AFRICOM situation in Mozambique. And you can see that, here we kind of just show this for English in this demo. But, there are lots and lots of messages. So even in English, you can see that there's news, there's social media, there's retweeting, there's all kind of things going on here. And, it's very heterogeneous.
Is it all text data?
Yeah, they did try to do speech. I mean, the overall Thor project involved a little bit of speech recognition as well, and some imagery, but mainly it was text data. We try to focus mainly on text.
Okay.
Yeah. So what you just saw a little bit earlier was the Uyghur, which I was just showing, but we're back in the Mozambique. You can start to see that, there are situations such as, collapsed homes, right, and so on. And so the primary need really is shelter. So shelter in Mozambique is a main need, which is also what the machine learning is predicting. Also search and rescue. You can see that we can draw a rectangle around the area, right? And we can click on, anything pretty much over here, and it would zoom you into the area that you're interested in. You can click on the different need, and then it will just show you what those needs are. So here we clicked on the medicine need, and it's showing you that medicine need is very focused on this province. Then you can go back and look at all the other needs over here, right? So all this stuff is happening. I'll stop here because it's just the rest of the presentation is very similar to what you see here. And so, this is all, you don't even need a training course in this, right? It's kind of, if I gave you this interface, once I told you that, okay, you can click on anything, this is how you go back, this is how you move forward, these are some of the things available to you. It's like less than 1 minute kind of thing. Like just by watching this video, they would probably just learn what they could do. And, and I do want to point out that one of the things we learned while we were doing this is how important this raw data really was. I mean, in this case, this is already in English for this illustrative use case, but for the Uyghur one, what we would be able to do is to not only show you the translated version, but there would be a tab over here where you would be able to see the original version. So if you had a subject matter expert or a local, which you would have in a real situation, then you can, before you take a drastic decision, you could get them to actually read the message. And, it allows you to focus on the messages that matter. And there's a number of other things that we can go into. For example, you can see there's a lot of duplication going on over here, right? The same message is showing up, but it turns out we have algorithms that would cluster the messages so that you could see the unique needs and you wouldn't see like a long list of duplicate messages or retweets. So this way you can identify many needs in a very short period of time. So this is something that I was very involved in. And in fact, I did my PhD in a very similar area. And that's why I was in charge of that part of the project, which is how do you actually match tweets and messages and entities so that the group that emerges from that refers to a unique situation. So how do you group everything together so that each group is a unique situation? So this was a problem that I worked on a lot over those 2 or 3 years, applying fairly advanced machine learning for that. Yeah.
So is it machine translation or what exactly are you predicting? Because you're taking the Uyghur text and you're translating it into English, and then you're classifying it into, what kind of need, what kind of, crisis it is.
Yeah, several things are happening. So, now let's go into this architecture and in what order it would go. So the TA, by the way, over here stands for task area. So these would be different teams. So you can see there's TA1, TA2, and TA3, right? And so the DARPA divides up the teams in this way often. And, T stands for task. So there could be multiple teams working in a task. Here there was one team that was responsible for gathering the data. So this would be, something like Ushahidi. So there's a platform called Ushahidi, which is very popular in Kenya. I think it was originally built by citizen scientists to get election violence data from
Oh, wow.
grassroots in Kenya. So there are platforms like that, and in those parts of the world where there are entrepreneurial or enterprising individuals who really care deeply about the problem and use open source to try and gather data. So in this case, there was a team that was doing that.
But how are they doing that? How are they aggregating all these different kinds of, there's just scraping?
You could be scraping, you could be
Whatever.
monitoring news websites. They're like, it depends on the situation a lot of times. There may be a dedicated SMS portal. It really depends on the situation. The infrastructure is very different in different places.
Yeah.
Right. So it's kind of, that's why there was a team that was supposed to do this for each situation. And
then who's cleaning it and labeling it and everything? That's all happening from that same team.
no, so this is all automatic. So they would just gather the data, and then the data would go into the streaming API. So they're not doing any intelligence on this just yet. So this is going into a streaming API. And then, the next step really is what we call clean text extraction. What this means is that, there's a lot of garbage around the text, metadata that is not useful, it's sort of maybe XML snippets of code, what have you, right? It would extract some clean text. So you would get a span of text. Now, this would go into the TA, this other task, teams working on this task. And this is what we call the LTDE. So LTDE is a language technology development environment. This is where all the natural language processing would be happening. So this would include machine translation, so it would be getting translated into a language like English. But they would also be doing other things. They would be extracting entities, like who are the people mentioned in the message, who are the what are the relations in the message, right? So if some person is trapped in a building, trapped is not an entity, it's a relation, right? So the building is an entity, the person is an entity, but trapped would be a relation. So this is like a relation connecting two entities. That's usually how we define in a knowledge graph. And you could extract sentiment. I mean, there are other services, there's speech coming in. They also had a way to do speech transcription, so they could, convert to text, just like it happens in a Zoom call, right? And then you could apply NLP on the transcription and so on. So, this is more like, the intelligence that would be extracted from the text. So it's like text plus plus. That's how we think about it. And then the text plus plus, right? So you get the text from the web service API, and then you send back the text, but with all the other stuff on it. Now, this other stuff could be noisy because you have thousands of messages coming in, and all of this is automatic or semi-automatic. There may be some manual work involved, but it's very minimal because you're on a clock, right? It's happening very quickly, and you can't like label every message. So, this is a different kind of machine learning where you have to like figure out, okay, what is the message that it's best, that will be marginally best for you to label so that you can improve overall accuracy of your system and expectation. There are tools like active learning in the machine learning community and so on, number of more advanced tools as well. But once it comes in here, now you have the text plus plus, and we can put it into the knowledge graph, right? Because now we have the text, we have the entities, we have the attributes, we have sentiment, we have other things. So it can go into document cache. This is where the raw text is, and there's an infrastructure called Neon that was used for that. There are other things that could be used as well, like MongoDB and so on. The knowledge graph used our technology, which was called DIG, domain-specific insight graphs, that we had used for human trafficking, to fight human trafficking. This was again built to another DARPA project. Could be Neo4j also. So it doesn't have to just be, our technology. At the time, Neo4j was not very mature when we were doing this, but it could be Neo4j. And this is really where I think I came in. So this is where I was doing a lot of the analysis, including network analysis, route planning. Entity resolution is a problem I was just telling you about, that, how do you resolve entities and events so that they are referring to a unique entity or an event? This is a problem that is 50 years old. It shows up in every single domain. So in Amazon, which products are referring to the same product, right? There may be multiple third-party providers providing the same product with very minor differences. Sometimes there is a very small difference, like, same brand of t-shirt, but red versus black, right? You don't want to count them as totally unique products. They are the same product with a different attributes. So that's also a kind of entity resolution. You see it with duplicate web pages on Google. You see it in patient records when you are doing data linking. So this is a very common problem. And in this case, we wanted to know that if you extracted Donald Trump from a message and you extracted Trump from another message, that they are in fact the same person, which they don't have to be. Maybe it's a son, right, who has the same name. You have to look at the context around the message and so on. So, it's fairly advanced machine learning in a way. And And then, the data access API would feed it into the interface. And behind the scenes, there would be a querying and filtering and so on. But the front facing would be the kind of interface that I just showed you. This evolved over time based on the needs that we heard about from many of the users. Initially, the focus was on route planning, and it kind of looked a little bit, or hotspot detection, which is the one on the left-hand side. Route planning is on the right-hand side. Eventually, what we learned was, the thing we showed you is kind of what the final product was, because that's what we learned is what is needed by the folks that we were trying to roll this out to. But this was all evolving over time, but everyone was working on these different components at the same time, and we had to communicate through Dockers, through API, and so on. So it was quite a project with a lot of communication and different teams and pulling things together, and finally getting this interface that could be demonstrated and transitioned.
And that communication, this is all happening real time, right? So this is, time is of the utmost essence. So
in the final product, it's happening in real time. Before the final product gets developed, it's when we were building these things together, so what DARPA likes to do is they have a very evaluation heavy methodology, which I am very much in favor of. I think it's really a forcing function for making sure that you are making progress, and not, the answer is not, give us 3 years and then we'll come back and tell you what we did. It's every 6 months, they have evaluations. This is also why we like to have different teams to actually do this work. So in the evaluation, everyone had to bring their latest research together, and there would be APIs that would be defined either by the government or by the TA3, which was the most external team, right? They were responsible for the data, so they were not involved in the systems building. So they could be neutral, right? They could come and say, in some cases, we said it in the TA2 that hey, this is the API we need. We went and told the TA1, this is the API, this is how you have to give it to us, whether it's a Docker or some other way, but we need you to give us the data that you are generating in this way, and then we will put it in the knowledge base and take it from there. So there was a lot of, there were a lot of meetings, lots of discussion on how to define the API properly, all that kind of thing. So there was a big social element to it. It wasn't very streamlined, I would say, the whole discussion. I mean, there were a lot of iterations, and it was very much a social process. And I wouldn't say it was super streamlined. I've never known a system yet, or an architecture yet, where it has been very streamlined, where it's very plug and play. And so that's why I'm excited by what you guys are doing, because I think that you could maybe have a lot of impact in some of these domains where it's very difficult to compose and from different teams and plug and play, figure out what's going right, what's going wrong. I mean, it's a tough problem, yeah.
Yeah, the communication between teams is something that we're definitely looking into with our platform, as well as scaling. So how this seems hard to scale, yeah? Or how did that work? I think the talked about that too, the need for rapid scaling.
Yes, you're right about that. This is why I think one of the very good things that DARPA did was that the streaming API, they could have said, well, if they had not known it in advance or had anticipated in advance what the scaling problem could have been, they would not have actually put the streaming API. This may seem like a small thing, but it really isn't, because everyone who works in machine learning pretty much knows when you have like an online paradigm where things are streaming versus an offline paradigm where you have like a batch data set that you train a model on, and then you just apply that model also in a batch setting, are two completely different beasts. So when you have data coming in and you're trying to update your models in real time as they are coming in, it could be that there's a bootstrapping phase, the first 1,000 messages. It's not, you can build your initial model on that, but then at some point it does have to become streaming very quickly. And it places different infrastructure demands, it places different technology demands, so when they were doing their, as one example, like if you know that you can only look at 1 or 2 messages when you're extracting an entity, that you can't rely on a lot of context, right? It's only the context of the messages you may have seen, and you're not allowed to retain those messages. Those messages go on, you can't store them in this base. It has to go on to the knowledge base where it gets stored, and then you can't access it very quickly. So you can't rely on what you've learned before. So whatever you want to do, you need to do it now. When the message is coming in, you need to update your model now in an online setting. You can't go back and look at the message again as new messages are coming in, right? So this takes a different kind of design. And then the context is also very different, because when the new message comes in, you only have the context of the new message. You may not have the rest of the context to your model. So this makes my problem a little bit harder, because I know that there will be a lot of noise because they don't have the full context, right? So when they see the name of some location, like for example, if a disaster breaks out around, Paris, Texas, for example, there is actually a Paris in Texas.
Mhm.
And so when disaster breaks out around Paris, Texas, if Texas is not mentioned, then you get a message and it's saying that, oh, shooting happened in Paris. You might assume it's the other Paris, right? That's the most reasonable thing to assume. But then when I get the message, then I would have to figure out that no, it's a different Paris, and this is not the Paris that we might be thinking about. And so it would make the entity resolution harder. One of the other things we like to do in this knowledge base space is that if the entity has a Wikipedia link or some other link, we want to automatically link that, because that way we get more information, right? So if we know it's Paris, Texas, then we can link it to an external knowledge base, which has the latitude and longitude of Paris, Texas. There are open source knowledge bases that can do that, like GeoNames is one example. And you can get, Paris, Texas coordinates from that knowledge base, but you have to know it's Paris, Texas, not Paris, France. And so once we know that, we can get the lat long, and then that makes the visualization a lot easier, right? So, this is the kind of thing I would have to figure out, that can I actually do the entity linking? Do I have enough information? What do I need to get from the knowledge base till I can make a decision? And when I say I, it's really the algorithm, right? So yeah, this was a very interesting problem, then how can you do that in a streaming fashion? So that addresses scalability though, right? The big advantage of that is that scalability is not an issue anymore. Yeah.
So, and is there also an alert and detect feature to all of this too? So we like look for chatter, I guess, circling, around Paris.
Yeah, no, absolutely.
When a shooting has taken place, or is this something like a system you deploy when you know that there has been an earthquake?
No, they had alert systems. There were two different kind of alert systems. One was a kind of system that could be integrated at the back end. So it would be like a replacement for this PA3 real-time data, where, let's say you have access to the Twitter API, and then you may be monitoring for certain keywords, or there's a news source, breaking news source that you're monitoring. And, you can set up alerts. It's really not all that different from how Google News and other people set alerts. There's a certain way to do it. Basically, you're monitoring a source and seeing when a word or a feature comes alive, right? And there are ways to do that. I mean, it doesn't happen at the millisecond level, but nor does it need to, right? But you can periodically monitor and automatically. And so that would be one kind of alert system. The other kind of alert system was you already know the situation that you are interested in. And so you're getting data already. The filtering has been set up. So you're getting raw data already. But now you want an alert system in the GUI, in the graphical user interface. And there was a way to set that, if a evacuation need arises, if a unique evacuation need arises, or something happens, there was a way in the GUI. It was kind of, rudimentary, but it was the kind of thing that the non-technical experts wanted, right? Which is that, hey, can we actually set rules in the knowledge base so that if some location flags up again, or there's a tweet with a certain word, etc., that, this would be brought to our attention. And so we did have a feature. It was kind of like a bell icon, just like you see in many other applications. And you could actually set rules in that, very simple rules, like, location equal to this, and, word equal to this. And it required some training. That feature required some training on the part of the users, but it was really easy. It was rolled out in the final product, if I'm not mistaken. We didn't actually work on that because it was very mechanistic. It didn't really involve machine learning as such. It was pretty much just, okay, if you specify rules, if they get triggered, it could be brought to your attention. And if not, then, there's nothing to learn, right? Because they wanted like clear rules that they could specify.
Mm-hmm. Will you tell me about active learning and how that factors into this?
Yeah, it was really interesting. I mean, it was unique, I think, to this project, the way that it was done. So it tended to happen a lot in the translation. So, these low resource languages, as I said, right, there really isn't a lot of, the assumption is there's no computational tool really, right? So you may have some very rudimentary translator, like a dictionary, would be a very good example. Usually there would be a dictionary, like, this word or thesaurus, where that, okay, this word has these synonyms and this word has an English translation, a dictionary translation. So the assumption, okay, I'll give you a dictionary translation. I can also give you a lot of unlabeled text, right? So these are the documents written in that language, maybe the country's constitution, maybe news articles, other things. So, but these don't have a translated version. These will be like raw text in our language, but for the machine learning, that is essential, it turns out. The modern machine learning, if you give it a lot of unsupervised, what we call unsupervised, unlabeled, untranslated data, the neural network can really learn a lot, even from that, just by seeing that for each word, what are the words that are occurring around it. And it can build a model, what's called a language model. So this is a model of that language. And then it turns out that once it does that, then you can seed it with some of the dictionary translation. So this way, now it starts to get connected to the English, right? In a very rudimentary way. It's not like a sentence to sentence translation, but it's like a word to word translation. And you have a very good model of the local language. And you also have a very good model of English, right? So you have two very good language models. And now you start to get some anchor points because of the dictionary words, right? Now the next thing is, okay, so that's good, but we need to do even better, right? So the even better is that, okay, now can we show some messages to a subject matter expert, which for us would be like a local language speaker for machine translation purposes, right? And then get them to tell us, are bilingual, and get them to tell us what the meaning of the message is. And so this way, now we get some sentence translations, and that serves as an even stronger anchor point. And now you can get a translation model out of that and hopefully improve it over time, right? So the real question here was which sentences, as I understand it, I'm not a machine translation expert, but this was my understanding based on how it's done and what was presented, which is that which sentences and or any other inputs, whether they are phrases, sentences, words, do we actually send or ask the local person to translate for us. The way that DARPA controlled for this in the evaluation was that they allowed a very limited number of local translation consulting hours, if you will, when they were doing the evaluation. So they said, well, to be fair to all the teams, right, it would be like maybe 2 hours, 3 hours, something like that. So there would be a very narrow window of time when you would be able to make use of that resource. And so the question was that under those constraints, can you do a good enough job that we can get something useful eventually, right? So, and I think they did really well on that. This was a very, I would not call it a problem that was solved, but they got close enough that by the end of it, they really could, I would say within 72 hours or less, come close to having a system that did seem to be giving useful outputs. And then we could use them to, cluster things together. And then they would go on the GUI and people could play with them. So at the end of it, the output was very useful. It's kind of what we found in many of the domains that this was tested on.
So is 72 hours fast enough?
We have to work with the technology, right? Yeah. So ideally, of course, it should, we would want something like a universal translator. And I think they are moving towards that. That is their goal. And they are closer than many people think. It seemed like very Star Trek technology, the universal translator. But I think the universal translator will be here in, it's already here in a rudimentary form. I suspect that. So it's also, I should also say that, in a way, these are like different versions, right? So you can say that, okay, within 24 hours, you will have a translator that is using the dictionary encoding, right? So you train the model and then you have some anchors to the English model, and you may be able to actually get a translation. But then, once you get the outputs from the local experts, now the translation starts to make more sense. So, I would argue that, within 72 hours, it might seem like, okay, maybe it's not long enough in a way, but, within those 72 hours, it's going to take you that much time just for the team to get there and for messages to start coming in. The locals will obviously be doing something as well. They're not going to be sitting still, right? They're going to be trying to gain situational awareness and gather information. So I would say even in practice, the 72 hours is not such a long period of time as it might seem, because things really move quickly, right? In these kind of situations. The idea is the technology gets better over time, right? Like that was the ambition of the program. Before the program, even that was considered impossible. So it was a very moonshot problem. The translation was at the center of the program. I would say the other stuff was what made it practical and useful and involved its own brand of AI. But the translation, in all fairness, even though that was not what I was working on, but I have to give credit to the translation teams. They really made the program successful, I think, by improving their models with each evaluation season.
So what about reasoning?
So the reasoning would be things like, what you saw on the GUI, right? So if there were two different, so reasoning and inference go hand in hand. That's the first thing I should say. So a lot of times people think of the two equivalently in practice. So the inference would be things like figuring out, which messages are medicine need versus shelter need and so on, right? So this is more like machine learning inference where you're classifying the messages. The reasoning would be more, I would say, related to the entity resolution, right? Which is that if if this entity is trapped in this building, then it is likely that 1 hour later, if I again get a message saying that this entity is trapped in this building, that the two are actually one and the same, right? So you can sort of see here that the line is blurred between reasoning and inference, because that can also be framed as an inference problem, or it can be framed as a reasoning problem. That okay, I reason that it's the same because the time period is too short, and it's unlikely that the same entity would be trapped in the same place in like two different situations, that we evacuated them and then they went in and again got trapped, right? So it's I would say that probabilistic reasoning is kind of what we were doing, and the probabilistic reasoning is just one step away from inference, which is also probabilistic. So probabilities were very important over here because there was a lot of noise and uncertain information. So classic reasoning, which is like logic and saying that okay, if A is equal to B, then B is equal to A, is that, just to put it simply, right? It's rule-based kind of reasoning does not really apply over here. It would not work over here. This was like the 1980s kind of AI, where you had the rule-based expert systems kind of reasoning. It was implemented in certain organizations. It's like, workflows, who needs to approve your reimbursement and then what needs to happen, like that kind of thing, which we still see. I mean, we don't consider it AI anymore, right? I mean, that's just considered technology. But yeah, that kind of thing does not work here. The logic and the expert systems don't work over here. I think the probabilistic reasoning, probabilistic inference is what works here in practice. Yeah.
Hey, Mayank, can I ask a question more about the system architecture and some of the what I might consider could have been issues that you had to figure out? So part one is it seems that there are a number of different individuals with different talents that are kind of trying to work together across these different parts of the system. And number two is that there are a number of different models as well, a number of different systems that are being stitched together as well.
That's right.
And there's like these multiple dimensions of heterogeneity that you're working across. And that's not, I mean, the teams aren't designed, people aren't designed to work across so much heterogeneity and working across a single problem, right? So
yes,
we don't see this very often outside of like these larger AI focused projects. People trying to connect so many different pieces together in a streaming fashion, which is what you guys were doing. So I guess I would imagine this would have taken a long time and a lot of effort and a lot of churn and resources and a lot of key persons that had to do and pull some strings and such. Can you tell us how that experience was, and feel free to tell us how painful it was as well, because it seems like that's something that was not easy.
Oh yeah, I mean, so the two statements you made are absolutely correct, and so I want to restate them because they are very important. So the first one was the teams and the people, and you're absolutely right. We often underestimate heterogeneity of people. So this is something that does not get talked about enough, right? I mean, there's some assumption that everyone has the same level of skills, but that's not the case. In fact, I can tell you that even within the green boxes, which is Thor, I was working with another company, and this company was building the UI and was doing a lot of the integration I was building the web service API. And even within this company, there were different degrees of motivation. Different, within my own team with my students, there were some students who were not experienced, and didn't have a talent for the engineering side. There were other students who did have the talent and were in fact interested in the engineering. So I think that the real, as product managers, project managers, just managers in general, engineering managers, what makes them successful is how to work with the heterogeneous group of people and talents. And I still feel like that is underappreciated. Not a lot is said about that, including in industry. And it's everyone knows it exists, but it's just not. I feel like we don't have a language yet for talking about that, to be honest with you. And then the second part are the systems, which are very heterogeneous. In each of these boxes, you have a different system. Not only that, but for some boxes, you could have more than one system, because what DARPA likes to do is it's not just one team that is working on each of these things. So it's true there was one team working on the data, and we were the core team. So this was one team. But the TA 1.4 that you see here, the LTDE web services, this was, I think, 3 or 4 different teams. So when I say a team, what I mean is a funded unit. So a team here could be 3 or 4 institutions. So when I really say a team, what I mean is a contract, right? So there were 3 or 4 contracts for, let's say, TA 1. And within each of those contracts, there were multiple institutions. So at USC, there was the 8th floor, and then there was the 9th floor. So 8th floor was me, and I was working on this with the company, and that was one contract. That was the TA2 contract. And then there was another, the 9th floor, which was working on the machine translation and the LTDE, and they were working with Columbia University, with a couple of other places, and that was another contract. So there were 2 different contracts that were awarded to USC for this, which is not unusual. And so, there were a lot of times, believe it or not, I mean, not by design, but simply because that was the way things were, is that I would run into the 9th floor people, and, we would be very friendly and so on, but we would have the real technical discussion when we showed up for the DARPA meeting in Washington, DC. So we would go to Washington, DC, all on our own flights. Sometimes we would run into each other on the flight, and then we would have the meeting and the breakout groups, and we would have the deep technical meeting with everyone. And, there was a lot of discussion on APIs. Docker and containerization was a big blessing. I think containerization single-handedly was probably make this a lot easier, but it's not the final line in the story. I think it was just the beginning of the story, right? So, that was another one. Exchanging Dockers was not easy. A lot of times setting up these APIs was not easy. So yeah, a lot of back and forth. I mean, there was a lot of work done for these different arrows, for these different APIs. Again, I think there's a cultural problem that we often tend not to talk about these things or treat them as glamorous, whether it's in the research community, even in industry. I would say that it's, people who build the boxes tend to get credit rather than a lot of people who work on the arrows. And so there's something about the arrows that is not glamorous compared to the boxes. So I call it the boxes and arrows problem. There's a lot of work happening in the arrows, and we're not focusing enough on that. So it's a socio-technical problem. There's technology that can improve, and then there's culture and the way that we socially look at this that also needs to improve. But you're absolutely correct that all of that was an issue. The forcing function was DARPA. I mean, nothing talks like money, right? So when there's this organization that is funding you, and you have to do well, and you have to work together, there are PI meetings, you have to show results. It's really a forcing function. Like, you come in and you better have improved results. And if you don't, then you must have a reason. And the reason is not that you weren't able to get the engineering figured out and so on. So, those of us who lead these projects, we are really on the hook for delivering, and we get the money and we win the contracts and so on. But it's, rallying a group of people to deliver on some of these things is not always the easiest thing. And sometimes it's like a carrot and stick approach, as so often happens. It just depends, and you have to work with the strengths of the people that you get, but it's not an easy problem. I mean, a lot of times I'm just putting on my managerial hat, for which the business thing was helpful, and trying to get people to deliver, to give us, because internally also you're stitching things together, and then you have to Dockerize it, and then you have to give it to the next team, and then all of that, right? So yeah, it's a lot of work.
it seems like the solution to this heterogeneity problem and the complexity within it was partially, right? It seems based off of the authority, right? Authoritative direction that everyone had to follow. But then the active part of the solution seems to come from the philosophy of containerization, not just doing Docker itself, but even the stitching internally between all of your different parts.
Yeah,
There's
like
a
to
lot
give
to
an
be said.
example, to give an example, the LTDE, I remember that this was a Docker. This whole thing was a Docker from the USC group, and then from the USC and the other groups that were doing this. And then the Docker was, the API was basically a Docker, a handoff in a way, at least during the evaluation. And then, I was doing my own thing here, right? So this was a company was setting up the infrastructure and the UI. So, I would sometimes give them a Docker, but because I was working very closely with them, I would also just give them the Python code. I would be like, well, here's the code. There were even moments when we would not do that. They would actually give me the data. So they would give me access to the knowledge base and then would tell me that, okay, here's the knowledge base. And, can you run your algorithm on that and then add this field to the knowledge base, which contains the group ID that we want to use for entity resolution, right? And so there were a number of different ways that it worked. I mean, the containerization, I think, works well when the systems are bulkier, ironically enough. I think that sometimes it can be much simpler than that. And so that's why I said it's the beginning, not the end, because the truth is that the containerization could be a hammer that does not fit every nail. And sometimes simpler solutions work well. Yeah.
Have you had a chance to look into the Castle system and the Petuum platform, what we're doing with the AI OS and the universal pipelines system?
So I didn't get a chance to try it out, but I did go and look at the website and the, all of the description. And I do think that if it works as intended, right, if the final product works as intended, I mean, I can imagine that being supporting, almost a scaffolding for this kind of infrastructure. And this is common. I want to say that this is not uncommon, this problem. This problem is very common, even when there are two organizations. I mean, I'm working with other organizations now where this is not at all uncommon. If anything, if it doesn't occur, it's uncommon. Like even when you have two organizations, even when you have two groups in an organization, I'm working with an organization right now, and I won't give away the name or anything like that. But it's an organization that if I gave you the name, you would recognize it, and they are working on it. They are a leader in an important industrial sector, and I can tell you that in the organization, it's not unusual even to find groups that perhaps one group does not know what the other group is doing. Sometimes we see that the thing about USC is, or at ISI where I'm based, is that it's very streamlined. We're very pragmatic. We have a lot of experience with DARPA projects. So, we have an enterprise Slack and we are very communicative. So usually, when it comes to us, if we run into a problem, we know who to reach out to. But it's also not big, right? So ISI is, 400, 500 people. USC overall is many thousands of people. But, it's kind of easier with 400, 500 people to kind of know that, okay, this is the group. If I go and reach out to this person, they will connect me to the right person. So it's a two-hop kind of thing. But I have found that in industry, of all places, the problem actually really rears its head. And there's turf politics, this group wants to be the gatekeeper for this data, and so on and so forth. I mean, it's really surprising to me sometimes. And I often think that the reason why in DARPA circles and in academia, the reason why sometimes it can be very streamlined with the right team is because we don't have like a turf war, right? We care about the papers and the funding. And so papers are not turf war, right? Like you can be the gatekeeper, but it's not going to stop you. It's not going to lead to a paper, right? So ultimately, the only thing that will lead to a paper or an award or something like that is if you have a really good algorithm. And if you have a really good algorithm, you want to give it to the world, right? That's often what we do. The DARPA is a forcing function, right? Because it's like centralized planning. But even they have a very pragmatic system. There's a program manager that usually controls the program. The program is his or her baby in a way. They want the program to succeed. They know that they're not going to be around forever because in the DARPA culture, program managers don't stay around forever. They have to leave after a certain period of time. So everyone's incentives are aligned. Your incentive is aligned because you want to stay funded and you don't want to be cut. the program manager wants you to succeed and will listen to you. If you go and tell the program manager that, look, this is not working, we need to do this instead, right? They are very amenable to that, right? So I think incentive alignment is a very difficult problem. And then you have the technological alignment, which perhaps is an easier problem, but still a lot to be said. So I think that that's where your platform and company could certainly start addressing that, is addressing that problem. But I think there's a huge market in that.
Well, thanks.
Great.
Yeah, we've been talking about the scaling MLOps issue in general, right? That's what we talk about when we say MLOps.
Yeah.
Thanks for
I
all
mean,
the-
don't forget about the social element. I would say that, it's like you have the technology, right? It looks to me like you have the technology, or the technology is getting built. But if I may, what would really be something compelling is that if you also have a way, almost like a productivity kind of tool that is specifically designed to get many different people on the same page, so that they can negotiate with that technology as a scaffolding. Because it's a negotiation, right? When you're building this thing, there's a negotiation. And sure, you need the technology, and the people who are negotiating know that, okay, you gotta, we will use Docker, right? So maybe the first thing we agree on is, this is what happened, right? Which is that everyone came together. They were like, yeah, let's use Docker because that's the best we know. And we can all use Docker. So we'll all decide to use Docker. We'll define the APIs 3 months in advance. We'll do a handoff, a simple handoff 1 month in advance. And then the final handoff comes 1 week before the evaluation. And then we run the test and we give each other a thumbs up. Is it working? Is it not working? And so, there were these negotiations that were happening, and APIs had to be defined. And I remember we used Confluence for, documenting everything, but it was very much a social process. People would go and put things on Confluence and links and slides and, all kinds of other things. And the Confluence was like the central ground or record-keeping ground for the negotiation. But it was a negotiation, and the technology was just kind of like a supporting language for the negotiation. So I feel like if you have a better language and a more comprehensive kind of framework, and then you also have a way to actually get people to negotiate around, so like it's almost like slot filling, right? Like if your technology could do something where you're like, okay, these are the components we need. So let's draw the boxes, right? And then here are the arrows, and then, okay, this team is responsible for this, and then this, and then this. And then here are the APIs, and so let's start writing them down. And so if, that's my vision. I don't know if that's what you guys have in mind, but that's what really would make the MLOps really successful. It's almost like a collaborative architecture design with the technology serving as the scaffolding. Yeah.
Well, thank you very much, Mayank, for explaining your project to us, and your insights into MLOps was really fascinating. It's always fascinating to talk to you, but it was great to hear more about this. We are in a private beta right now, so we can tell you more about it if you're interested, or if any of the people in any of the projects that you're working on might be good candidates for us. Please introduce us so we can share more information about the platform that we're building.
Absolutely.
Yeah. I'd say that you not only explained your product, but at the end you kind of explained our product as well. So that's interesting.
Yeah.
I hope I did. I don't know if I was a little bit worried. Maybe I'm explaining the wrong thing, and they're gonna blame me for that.
Arrows,
No, this isn't what we do. Like you explained.
No, you know exactly what you're talking about, man. Don't worry. Okay, thank you so much.
All right, it's dropping off.
Bye, guys.
Talk to you again sometimes.